Hi, I'm Nicola Rennie, and welcome to my Use R talk about how to stop making spaghetti code. Essentially, a collection of tips about how to write better R code. I'm going to start with a very quick introduction to myself. So my background is in statistics and operational research, and I've previously worked in data science consultancy. I'm now a lecturer in health data science in the medical school at Lancaster University, where I'm interested in modeling routinely collected healthcare data, reproducible research, and data visualization, amongst other things. Now, in terms of today, what I'm essentially going to be talking about is writing better R code. And this talk has been motivated by a few things. One, that more academic journals are requiring authors to submit code, which is a good thing. Two, that more people without formal software development backgrounds are writing code. And three, that any publicly available code needs to be readable, reproducible, and easy to maintain. And so I wanted to talk about how you go from writing spaghetti code to working with good software development practices. It's essentially a talk about things that would have made my life easier if I'd known them 5 years ago. So let's start by thinking about how a typical R programming journey begins. It's often as part of a statistics or data analysis course, where you might be using R to do some coursework, and the projects you're working on are probably quite self-contained and straightforward, even if it doesn't feel like it. You might also have learned R on the job, where there's a specific project that you need to use it for, and so you learn R to do the project. Most people aren't taught R by people with computer science or software development backgrounds. And so we're not often taught good software development practices. And instead, we have to try and figure them out through trial and error when we start using R in real complex projects. And when you start working on a more complex project, for example, PhD research, by that point, you might be reasonably comfortable using R to do analysis, but you've never really learned how to manage R code. So scripts are getting longer and longer. They might be thousands of lines long. You might have lots of different R scripts hanging around in no particular order. And when it comes to sharing your code with other people, whether that's a supervisor, a teammate, or publicly with a journal paper, it feels really hard to share it because it's a bit of a mess and it's difficult to see what the code actually does. Essentially, it's spaghetti code. And the reason we write so much spaghetti code is because we're not really taught how not to. It's a big jump from using R in a classroom to using it in the real world. And you might not have a supervisor or a teammate who has a lot of experience of doing it either, so there's not always someone to ask for help. And if you inherit someone else's code, you might start writing in a similar way, making even more spaghetti. It's not something that's covered in depth in a lot of our textbooks, partly because real projects can vary so much, although there are an increasing number of excellent resources out there. And in terms of why do we care about this? You know, if your code works, does it really matter if it looks nice? Well, yes, it does. So both future you and other people will be grateful if the code you read is readable and understandable. Code that's easy to read and easy to understand is much easier to use. So how do we write code that's easy to read and easy to understand? Well, we share useful tips and resources that we found. We review other people's code. So what makes it easy to read? What makes it hard to read? And also by having other people review our code. That's something that's quite common in industry, but something we should definitely be doing more of in academia. And before we jump into some of these useful tips, I do want to highlight that I'm not saying you have to fix everything in your code overnight. Even just integrating a few of these practices into your code can really make a difference. So let's start with the simplest case. Okay, you have an R script and you want to make it better. So let's just start with one file at a time. Okay, so adding comments. It's something we all probably know we're supposed to do, but probably don't do enough of, or at least not the right type of comments. Okay, so you add comments in R using a hashtag, and I prefer to add them on a new line rather than at the end of a line of code. So this helps to keep all of the comments for a piece of code together. The comments don't need to explain what your code does. Okay? Your code usually does that by itself. But comments should explain why you did something a particular way. Okay? If you have code that isn't commented, you can figure out what it does by trial and error. But you can't figure out why it does that, unless whoever wrote the code also wrote down why. So if you look at this example here, it's a simple piece of code that calculates the mean and standard deviation of a column in the Star Wars data. Okay. On the left, the comments explain that the code calculates the mean and standard deviation, but the use of the mean and SD functions already tell us that. If you look at the same code on the right, it tells us why we're removing missing values from the calculation. When your code starts getting longer, it can be useful to add sections and subsections to your code. In the same way you wouldn't write a paper that's just one long piece of text with no sections, you shouldn't write R code like that either. So you can add sections to an R script using hashtags and dashes in a comment. If you use the Control, Shift, and R keyboard shortcut, it will create a section in your script. And this makes it easier to navigate long scripts in RStudio because it creates a script outline and you can navigate easily to a specific section. We should also talk about code style. Okay, so here's another example of some data wrangling code. So this code runs without errors and it returns the output that we want. Does that mean that it's well-written code? Okay. Here's the same code, but with a different layout. I think you'll agree that the second version is much easier to read. Right? Long lines of code that require sort of left to right scrolling is quite hard for our eyes to follow. But setting out the same code across multiple lines makes it easier to see what's going on, especially when you're using tidyverse functions. Putting each function on a new line makes it very easy to see that the code filters, selects, groups, and summarizes the data. Now, when it comes to making sure that your code conforms to whichever style guidelines you decide upon, linting is really useful. So linting is essentially about analyzing your code, but not running it. So it's a static analysis. So linting can check for stylistic issues, including things like checking for spaces between operators. So in the example here, it's not clear if we are checking that x is less than -3, or if we're assigning the value of 3 to x. So adding spaces makes this much clearer. It can also check for common errors, such as using a function argument twice. And it can do things like check for missing packages and lots of other things. And in R, linting is done using the lint_r package. So you can run the lint function, and it gives you a report about current issues within your code. So you can see here for the Star Wars example, it's telling me about missing spaces, lines that are too long, and using capital T instead of true. You can add a keyboard shortcut to lint the current file or package to make it easier to generate these reports. Now, these reports from lint_r are really useful, but they don't actually fix the code. They just tell you what you need to fix. So another package, styler, will style your code for you. It will add the spaces, replace the T with true, and so on. Again, you can add a keyboard shortcut to style active file to style the file you're currently working on. Now, the styler package can't fix everything that's found by lint_r. Some things just require human input, but they work really well together. Okay, so let's think about the slightly more complex situation where you're starting to have multiple R files and not just one. Let's actually imagine for a second that you do just have one R file that does all of your analysis for a project. This is fine, but it's not great. It's probably a very long script, and even if it does have sections and subsections, it's probably quite hard to navigate. It's hard to find a descriptive, useful name for a file that does lots of different things. Some things that are probably important and some stuff that's maybe less important. So let's start thinking about what the file actually does. If you're using sections, you've maybe already done that. So you might have a script that loads some packages, then reads in some data, does some data wrangling, makes some exploratory plots, computes summary statistics, fits some models, and then produces final outputs like plots or tables. So each of these different jobs can go into a separate script. So something like the layout on the left here would be better than just having one script. But actually, we can make it even better by thinking about what we call each of these files. Okay? The layout on the right is even better. So operating systems can sort things alphabetically. And this means that if you prefix the file name with a number, they'll be sorted in the order that they go in your analysis workflow. And this makes it easier for you to know which script you want to edit. Okay? You can add leading zeros to make sure that, for example, 1 and 10 go in the right order. You should also give your files sensible descriptive names. Okay? Exploratory plots and final plots is much more useful than plots 1 and plots 2. Computers also usually prefer files name to have underscores or dashes rather than spaces. Okay? Similar sort of guidelines can be applied when you're creating things like variable names or function names in R as well. We'll come back a little bit later to how do you avoid creating multiple files for different versions of code. So as well as multiple R scripts, you probably have other files for a project. Okay? These might be input files like CSV files of data, or output files like plots or documents. So don't just organize the R code, but organize all the files. Okay? So put your R code in one folder, create a folder for your data, create a folder for your plots, and so on. Again, name these folders sensibly. This might also be where you start to think about writing functions, if you haven't already, and separating out functions from other interactive code. This is quite useful if you at some point decide to convert your analysis code into an R package. It's also really useful to add another 2 files. So one is a README file where you write down what you're doing and what the requirements are to do it. So for example, the version of R, the packages you're using, and what your code is doing. Secondly, an R project file makes it much easier to write code that's reproducible, especially when you're reading in data from other files and have multiple R scripts. So on the topic of multiple R scripts again, it's useful to think about which scripts depend on each other. So in the example we're working with here, script 1 depends on script 0. You need to load the packages before you can load the data. Script 2 depends on script 1. You need to load the data before you can wrangle it, and so on. So here, script 4, the modeling script, depends on script 0, 1, and 2, but not 3. Okay? You don't need to rerun the code that makes a histogram before you can rerun the lm function, for example. Now, this is something that's useful to write down in a README file. If you ever need to rerun parts of your analysis, this will help you to figure out which bits you need to rerun. A better solution than simply writing stuff down is the targets package. So it's a pipeline tool for sort of analysis workflows in R. And what it does is it watches the dependencies in workflows and only reruns bits of code that it needs to. So unlike approaches that might source other files, targets also works with changes to data. And there are some nice functions to visualize the dependencies in your code. Now, this might feel like a bit of a jump from what you're doing now, but this comes back to what I was talking about earlier. Start with small steps. Start with splitting up your code into multiple files and figuring out what depends on what. Now let's end by thinking about how do you share your code with other people in an effective way. So imagine that you've written some code and you want me to review it. So you email me a file called code.r. Then maybe I add some comments or some changes and email you code back in a file called code Nicola comments.r. Then you apply some changes, add some more code, and ask for a review the next week. So you email me a file called code version 2. I add some comments or some changes and email you code back called code version 2, Nicola comments, and so on. Right? You can see how this becomes unmanageable very quickly. So how do we manage different versions of code, especially when we have multiple files? So the easiest solution is using Git. Git is a free open source version control tool. It's usually used alongside something like GitHub, GitLab, Bitbucket, or other similar options. So these are places to host online Git repositories, which lets people in different locations work together on code. Now, tools like GitHub or their similar alternatives lets you keep track of different versions of files without having multiple copies. This helps to avoid our analysis final and analysis final code files. It also keeps track of these changes after they've been accepted. So unlike track changes in Word documents, you can always see who did what when. You can ask someone to review your code, they can add comments and make suggestions, saving this problem of emailing copies of code back and forth. You can use it as a project management tool, so using issues to create to-do lists and setting deadlines. You can also set up automatic linting to help enforce a consistent code style. And although tools like GitHub are often recommended for collaborating on code with other people, there's no reason you can't use it on projects where it's just you writing code. In fact, I'd recommend it. It's useful to practice using Git on your own before you need to use it to work with other people. It's also easy to switch between having your code private or public on GitHub. So you can work on your code with your collaborators in private, and then when you're ready to submit a paper to a journal and need to make it public, you can do so with the click of a button. And if your code is public, you should think about adding a license that tells other people how they're allowed to use your code. You can also use things like git ignore files to make sure that sensitive files, such as data, are never uploaded to GitHub and made public. There are also some other considerations to think about when you're sharing code with other people, including thinking about which versions of R and different packages you're using. There's lots of different options for thinking about how to handle different software versions, including rend, Groundhog, Nix, Docker, to name a few. We don't have time to go into detail on these today, unfortunately, but they are definitely worth having a look at. Now, I just want to end by reiterating again that I'm not saying you have to go out and change all of your code overnight to make it perfect, but at least try to write down what's going on. So for example, if you can't get rend to work in your project to manage package versions, at least write down a list of R packages that you've used and which versions you've used. So I'm going to leave you with some useful links, including a link to these slides so that you can get access to the other links. So the Turing Way goes into more detail about reproducible workflows, not specific to R, but really useful for thinking about how you do research. And Crystal Lucy's recent book on data management has lots of useful advice, including on organizing and documenting data in projects. Building reproducible analytical pipelines with R has quickly become my sort of go-to book for reproducible research practices in R. And it covers some of the topics we didn't have time to cover in detail today, such as managing software versions. And Happy Git with R is a really nice guide for getting started using Git and GitHub in R. And with that, thank you very much for listening, and I hope to see some nice, tidy looking R code in the future.